So I guess just a quick update about the exam. Finally got the information there. As you can see, we're doing 10.1 right now, and that is the last section that's going to be covered on the exam. Try to get like one type of problem from 10.1 to not be on there. It's like, why are you bothering with that? So I'm just going to ignore that. 10.1, just figured it's going to be on there. None of these problems are going to be that hard. There's only one thing to do. You just take the limit, right? So I don't know what they're completely about. Yeah, so basically all the integration stuff from chapter 8. You just figure like 8.1, because UDU is going to also be important. So all the integration stuff all the way through this. It is going to be exactly the same as the last test, so buckle up for that. All right, just be used to not being able to have the back button, and it's all multiple choice, hour long. Same thing with signing up for WebEx, and we'll just proctor you with an extra phone. It went pretty smoothly in this class anyway, so I assume it's going to go about the same way. Yeah, I really can't think of anything else about that. Any question from you guys?
Can I get the date again?
The date is Wednesday.
No,
Yeah.
It's next week.
Next Wednesday, whatever that date is going to be, the 23rd, 21st. All right, so, I guess the last thing I should say is the homework. I will have all the 10.1 homework due on Sunday, and then obviously we'll start the new stuff on Friday, but that's not going to be due, so I'll just push that to the next Sunday. Tuesday will be a review class for the exam, and we'll do this, I think, the same thing with recitation. I'll let you choose between either the morning one or I'll make a separate one. That's a little later in the afternoon, or a little later in the morning anyway, and you can do that if you want to sleep in a bit. Otherwise, let's get through the rest of this last section, and then you guys should be ready to start studying. So, infinite sequences, just as a quick review here, it's just an infinite list of numbers, and we're just trying to see now if those sequences converge towards one specific number, or if they go up to infinity or grow infinitely large, or if they just bounce around and never settle down on anything. And there's really only one method for trying to determine this, and that's just take the a sub n, the thing that generates all the terms of this sequence, and just take the limit it as n goes to infinity and see what happens. That's pretty much it. Now, of course, limits and taking limits is not the easiest thing necessarily, right? As we saw in Calc 1, there's all sorts of different ways to do that, and so we'll explore some more of those today. Okay, so I think we ended last time with L'Hopital's rule, which I think most people know how to do that. So let's do some of these more smaller, obscure theorems. First one says this. If the limit as n goes to infinity of the absolute value of a sub n, if that ends up going to 0, then we can safely say that the limit as n goes to infinity of a sub n also goes to 0. And this is just going to be used for alternating series. See a lot of in this class, actually. So let me say it's used for alternating series. You're not really even going to have to specifically state this theorem, just be aware that it exists. Oh, I should say alternating sequences for now, not quite series. Like this one. So if you were looking at determining if negative 1 to the n times 1 over n, and let's say it's going from 1 to infinity, does that thing converge or diverge? Well, technically, in the limit as n goes to infinity, you've got something bouncing back and forth because negative 1 to different powers is going to go positive, negative. But you can see that the absolute value of this thing is just 1 over n. So the limit of that is going to go to 0. So therefore, we can say that the whole limit goes to 0. Not even going to do that as an example, just throwing it up there. Second one of the day is what we call the squeeze theorem, or the squeeze law for sequences, or you might have called it like the sandwich theorem or something like that. But basically, if we can bound two functions on top and below a function that we're trying to find the limit of, and those two things do the same thing, then we can squeeze the middle one into necessarily doing that thing as well. So here's the official way to word it in sequences. So suppose we have a sequence a sub n, which is always less than b sub n, or equal to. And that is also always less than or equal to a third sequence, c sub n, and this is true for all n. And In addition, we know that the limit as n goes to infinity of a sub n is equal to L, which is equal to, this is going to go off your screen, equal to the limit as n goes to infinity of b sub n. So basically the two boundaries both have a limit of L, and in that case, we know that the thing that is squeezed between them also must have that same limit. Then the limit as n goes to infinity of b sub n also equals L. So that's your squeeze theorem. We'll do one example with that and then move on. So here's an example of how to use this. Suppose you had cosine n over n as your sequence, going from 1 to infinity. Now, if you took the limit of this, you'd run into a problem directly, because the bottom would go to infinity, but the top would just not exist. So you technically get something that's not existing over infinity. And because we don't know what that not existing is, we can't just say it's going to 0 and use the previous theorem. So we actually have to do this bounding process and use the squeeze theorem. So what we know is that cosine n oscillates. The biggest it could possibly be is 1. And the smallest it possibly could be is -1. So we know -1 over n and 1 over n bound cosine n over n. And then we can look at the limits of these two things. We'll see they both go to 0 pretty trivially. Hard word to say, actually. But anyway, let's do it. So and you do have to state all this stuff. So since the limit as n approaches infinity of -1 over n goes to 1 over infinity or 0, and similarly, the limit of 1 over n as n goes to infinity is 1 over infinity, which also goes to 0. I lost a sign up here, but didn't have it. So both of these two things go to 0. So the thing that is between two things going to 0 also has to go to 0. So we can say at the end here, then the limit as n approaches infinity of cosine n over n also equals 0 by squeeze theorem. And we still technically have to state what is the answer here. So the sequence that we were asked to examine converges to 0. That would be your final answer. But this is the application of the squeeze theorem in getting to that answer. Usually people don't have much problem with this, but just in case you're more visual, basically what's happening here is this. We're saying cosine n basically always exists between 1 over n and -1 over n. So if these two things are going to 0, doesn't matter what cosine n over n is doing, it's always between them. So it also has to be going to 0. That's basically our squeezing the possible results into something that has only one possible value. All right, so then we're going to do the hardest one of these limit laws. It's really not a long section, so this is the last one. It's called the substitution law. Substitution law for sequences. I'm going to write it out, but honestly, I don't think you should be thinking of this in a theorem sense. The theorem is actually more confusing than the process is. So I'll write the theorem out, but then really we see this type of thing, we can understand what we're going to do. Here's the confusing theorem itself. So what they say is the limit then goes to infinity of some sequence, a sub n. Suppose that's equal to a known thing, we can actually evaluate it. And we have a function, so we'll call it function f, is continuous at the value x equals a, where a is whatever that limit was evaluated to be. Then, here's the results. The limit as n approaches infinity of f of a sub n is equal to f of a. So I'll explain what this is basically saying. We're saying if we took the function of the sequence generating term, all right, so whatever's in here, we just plug it into the function, then it's going to be the same limit as the function evaluated at whatever the limit was before, as long as this continuity holds. But where does it actually come into play? Sometimes you've got some very confusing thing. It's very hard to take the limit. But if I took the log of both sides, it would simplify down, and then I could go back, solve for the limit then, and then exponentiate back. Log and exponentials are continuous things, so it almost always works. So if that doesn't sound great to you, let's do a few examples and sort those. So suppose we had this sequence. N to the 1 over n, and the question is basically as usual, does the sequence converge or does it diverge? So the first thing you should note is the limit as n goes to infinity. I mean, you always pretty much just start at like, can I just take the limit? It's not going to work here, but can we try it? And I get n to the 1 over n, which is infinity to the 1 over infinity or infinity to the 0. And that's undetermined. Okay, so we're stuck. This is indeterminate form. I'll just note that we are stuck at that point. We've got to do something else. And the something else is if I use log rules to simplify the fact that there's this power to the base, then I could actually take the limit, probably, and work back to find out what the limit of this original column would be. Okay, so we're going to take the log of the limit. And what we're going to do is, what I would say do actually, is set up the limit and set it equal to what you want it to be. And by that I just mean pick some letter. Usually I'll call it L. So I can say the limit of this thing, the thing that I'm looking for is L. Now I'm going to rearrange it by this substitution law. And we'll solve for something that's related to L and then solve back for L. So the thing we're going to do is take the log. So limit as n approaches infinity of the natural log of n to the 1 over n is equal to the natural log of the limit. And here I could use my log rules. If you recall, if I have a log of something to a power, that power can come down out in front as a coefficient. And now I've got the limit as n approaches infinity of 1 over n log n. It's probably good just to keep writing ln L over here on the other side, but we won't touch that side until the very end. So now we basically have ln n over n, which has the form infinity over infinity. So I can use L'Hopital's rule at this stage. I'll just say my L'Hopital's rule on the left-hand side, this is equal to the limit as n goes to infinity of, okay, so derivative of the top will be derivative of log n, 1 over n. Derivative of the bottom is the derivative of n, which is 1. So I just get limit 1 over n. That clearly goes to 0. So 1 over infinity, which is 0, is equal to ln L. So I've solved this new limit. It's not exactly what I was looking for, but it is the log of the thing I'm looking for. So then I just need to exponentiate back, basically just solve for the L, and then I've got the original limit. So at this point, I'm just going to say to solve for L, it's almost always just going to be the inverse thing of what you just did. So we took logs, and now I'm going to exponentiate back. So e to the 0 is equal to e to the ln L. Of course, e to the ln, right, that's designed to cancel out. Anything to the 0 is 1, so we get 1 is equal to. That's it. So this limit that was indeterminate actually does come out to 1. And then we should still say, the sequence converges to 1 as a result. Right, always put at the end whatever the conclusion is. And so you can see why you don't really need to think of this wording of the theorem itself, right? It's just pretty much taking logs and using log rules. That's all you really need. Any questions? Yeah.
So, for the exam, we're going to have to figure out for ourselves which theorem to use.
Yes.
They're not going to tell us.
Yeah, I doubt it. Yeah. Now, there will be two different things. Assuming everything stays the same, which right now I don't have any reason to believe it won't, and it's multiple choice. The good news, I guess, for you is you can afford to be a little bit on the sloppy side. But for the quizzes and for normal exams, you really have to make sure that these are basically written out as proofs. So make sure that you write what theorem you're using, or what conditions you're using, and the results, and everything is shown very clearly with all those steps. Yeah. I think what a lot of people forget, I've seen in Calc II, I want to just talk about briefly, is the indeterminate forms. So in limits, the following things are considered indeterminate, or the following forms. This really isn't in this section, but I just find a lot of people have forgotten them. So don't write them down as I do them, because I'm going to put up a bunch of random forms, and some of them won't be indeterminate. We'll just discuss them as we go. So suppose in a limit, let's do the first obvious two. Infinity over infinity, and it could be plus or minus, and plus or minus 0 over plus or, there's no plus, 0 is 0. 0 over 0. Both of those two things we know to be indeterminate, and both of those things lead to L'Hopital's rule. Okay, some people ask, what about the other? Can we mix and match the zeros and the infinities? And the answer is no. Anything else besides those two is not indeterminate. Let's see why. So suppose you had 0 over infinity in a limit. Why is that not indeterminate? It's just going to 0. It's actually both halves of the fraction are forcing us to 0. Anything over infinity pushes us to 0, and 0 over anything pushes us to 0. So this is just going to 0. Same thing with infinity over 0. What's that going towards? What's that?
Infinity.
Yeah, it's going to be infinitely large. Now, technically, it depends on the signs here, so this could go to plus or minus infinity, but you just have to be careful with that. Right, the 0 could be a positive 0 or a negative 0, we'd have to see. But either way, it's not going to be indeterminate, it's just going to be an infinitely large in magnitudes thing. So that's not indeterminate. Contrast that with this, where we don't know what's happening, right? Those two cases, both halves of the fraction were pushing us in the same direction, but here we don't know, right? Infinite in the numerator means anything times infinity is infinity, but anything divided by infinity should be 0, so they're pushing in opposite directions and we don't know which one is pushing stronger. Same thing with the 0 over 0. Multiplication by 0 should take us to 0, but division by something tiny should take us infinitely large. So which is winning? That's what L'Hopital's rule figures out. Okay, that's the first big case. All right, how about some of these? How about 1 to the infinity power? Would you say that that is indeterminate or not? And when you want to think about indeterminate, you just kind of think to yourself, are things being pushed in two different directions?
It's just one, right?
You're saying this is equal to 1? Well, we don't necessarily know if this was both in the limit, right? So if the limit causes this to go very close to 1 and this to close to infinity, then what is something, even if you had something very, very close to 1, like 1.00001, what would be that to the infinity power? It would get bigger, right? It would explode, no matter what it is. It has to be exactly 1 for this to be. So in this case, this is indeterminate because this could be very, very, very close to 1, but not exactly 1. And that to the infinity power would make it potentially huge. So the two things that are pushing in the opposite direction, 1 to any power should be 1, but something to infinity power should be infinity. Okay, so it's a little bit tricky. How about 1 to the 0 power? You say 1 on that one? Yes. All right, this will go to 1 because if this is getting closer to 1, well, anything to the 0 power is 1. Right? So it's all going to, it's just pushing ourselves to 1. So that's not a problem if we saw that as a limit. How about infinity to the 0 power?
Any number to infinity. Like any
Infinity to any number should get huge, right?
Mhm.
But anything to the 0 power should be 1. So these are actually pushing in opposite directions. So that is indeterminate. But see, it's good to go over these things because I think a lot of people never really thought too deeply about it. How about 0 to the infinity power? This is an interesting one. Yeah.
Logically, I would like to assume it's 0, but I'm guessing.
All right, well, let's play it out. What do you guys think? Do you think this is indeterminate or do you think it's going to 0? Okay. So the 0, it could be something that's a little bit off from 0, right? But let's consider what's 1/2 to the infinity power? It goes to 0, right? Anything that's less than 1 to the infinity power goes to 0. So as long as this is anywhere close to 0, it's going to 0. So this one actually is not indeterminate. This one goes to 0. And you can see why you don't want to memorize this for sure, right? You want to just be able to think about it and logically say, like, what's actually happening to these functions. That one's a good one. How about, well, this one's kind of easy, but infinity to the infinity? Yeah, that just blows up, right? They're actually both taking you the same way, both taking you to infinity. Infinity to the negative infinity, that just takes you to 0, right? Because this is just 1 over infinity to the infinity. So it's just getting rid of this. So those are all fine. How about 0 to powers? 0 to the 0. Indeterminate. Because the 0 to any power takes you to 0, but anything to the 0 power should take you to 1. So those two things are fighting in opposite directions. 0 to the first power, that's pretty easy, right? That's going to 0. 0 to the infinity power, that's a problem. Or no? Yeah, that's going to go to 0, so that's not a problem. So 0 to 0 is the problem one. I think these are the main ones. But I want you guys to see why these are indeterminate and why the other things that we kind of went over and rejected would be fine. Now, I'm going to just because I'm feeling like a little more theoretical today, there is one exception to this, I guess. This is all assuming that all these pieces are going to that in the limit. So, for example, suppose I had limit as n goes to infinity of n over n plus 1 to the n. Okay. Notice that in the limit, the argument is going to 1, and the power is going to infinity. So this form is 1 over infinity. I'm going to say that this is indeterminate. However, there's a difference between that and this. What if I was tasked with the limit of 1 to the n? So this also appears to be 1 to the infinity, right? Do you see that there's actually a difference between this one and this one? This one is in the limit of 1, right? It's not actually a 1. It's just getting really, really close to 1. This one is literally just 1, right? It's literally the number 1, and the number 1 to any power is 1, so this goes to 1. So and there's a lot of subtleties with limits, and I just kind of wanted to go over them all with you. This kind of stuff does show up. If you don't master this, it's not going to be the difference, between failing and not failing, or doing pretty fine on Calc II exams. But if you want to be someone that's mastered it all, then these little trivialities will be those little last difference pieces. A lot of times people are a little confused by this stuff, so I'm going to just check for questions. So someone asked infinity to the 0 power. These are all indeterminate. And so take a minute, look at those. Want to go over any cases again? Let me know. 0 to the infinity. Yeah, that's actually a tricky one. I think that's maybe the trickiest one. 0 to the infinity. So imagine we're looking at something like the limit as n goes to infinity of 1 over n to the n. Something like that. The thing here is this space is not exactly 0, right? But as long as you have anything less than 1, that number raised to the infinity is getting smaller and smaller and smaller. So it doesn't actually matter that we're not exactly 0, because 0.001 to the infinity goes to 0. 0.01 to the infinity goes to 0. 0.7 to the infinity goes to 0. So even if we're anywhere close to 0, that thing is going down. We can also see it here when we do an example. What happens is because the numerator is obviously bigger than I said it backwards. The denominator is going to be bigger than the numerator because it's closer to 0 than not. And if I distributed the power, I can clearly see that the numerator is going to be dwarfed by the denominator here and go to 1 over infinity. Go to 0. So this always, no matter what leads to that form, is always a limit going to 0. Yeah. Well, then that's fine too, right? Like if this limit was, I was just saying, what's the limit of 0? Yeah. Then every single term is literally 0. Anything else? Good stuff to explore a little bit. This borderline case where I said it's like an actual number to it, that's not going to happen very often. But it will potentially happen at one spot in one section in our class. So that's why I mentioned it. Not for another month, though. All right. There's one more indeterminate form. Oh, there's 2 more. Okay, so there is also this. If you have infinity minus infinity, that one turns out to be annoying. This doesn't really get solved like the top 3, like these 3 cases right here. These will all get solved by this, what do we call it? The substitution law is probably the best way to go about that. That will take, by log rules, it will take the power down, and then you can get rid of that. Infinity minus infinity is just like the tough one. You just kind of have to play around with it. Sometimes you multiply top and bottom by a conjugate. Sometimes there's some other algebra you can do. But that is a problem. And the last problem is if we have infinity times 0, which actually comes up a decent amount. Again, we can see that pulling in 2 different directions, anything times infinity should be infinitely large, anything times 0 should be 0. So where does this go? Any suggestion as to what you would do if you got that in your limit? Put up like an example here. Limit and goes to infinity of n times e to the negative n. You can see that this part's going to infinity, and e to the negative infinity is actually, e to the negative infinity is, anyone remember from calc what you do on that?
Is it a log rule?
The log rules are not going to really work in this case because you'd end up with log of n times e to the negative n. So I can't really bring this down out in front. It's not the power of the entire argument. I could start to like log n plus log e to the negative n, but that starts to get messy. So logs is not really the way to go there. Yes, that is the key. So I'll just put the answer here, which is rewrite and do L'Hopital's. It's actually just a L'Hopital's in disguise, because I could take one of the terms and instead divide by its reciprocal, and then I get 0 over 0. And then you can go up there. Or I could have done n times e to the n and get infinity over infinity. So either way, just rewrite one of the pieces and it will be in L'Hopital's form. Guaranteed. So that's the last of the indeterminate forms I wanted to talk about. And with that in mind, let me give you one to try out. So do the following sequences, converge or diverge.
Wait, Professor. Just so I can get this clear, the indeterminate forms, they're not actually zeros. They're like a placeholder for functions that are approaching zeros, but it's not actually zero, right?
Very well said.
Okay, because that was confusing me because I kept looking at 0 and I thought that 0, like, okay, yeah. Thank you so much.
So that was like the one example I showed with the 1, right? If this was a literal 1, it would be different. And you had a very well described terminology there. You said like this is a placeholder for 1. It's just approaching it in the limit. So yeah, this is all placeholders. And I'm seeing now there's a couple questions in here. So I kind of wasn't looking and didn't see some of these questions. Does anyone still have a question? Nicole, did you want to do the 1 to infinity again? That seems to be the one that's missing. You got it? Okay. All right. Well, just let me know if, or you guys can speak up if you want me to do another thing. Otherwise, try these 3, I guess. 1, cosine 1 over n to the n power from 1 to infinity. 3n cubed e to the negative 3n from 1 to infinity. And lastly, this one's a harder one, ln 2n plus 1 minus ln n from 1 to infinity. We'll do that last one together for sure, but do try and get these first 2. First one should converge to 1. Second one should converge to 0. And the last one should converge to the natural log of 2. Mike says, do the 3, does it even matter in the other one? It may not matter in some problems, right? So you're asking like about this leading 3 here, right? It turns out in this problem, it doesn't matter at all. Whether that was there or not there, this was going to 0 either way. But imagine this thing was going to 1. And if you had a 3 there, it would make it converge to 3. So you can't just say beforehand, I'm going to ignore a constant because it very well may make a difference. If the limit ends up going to 0 or infinity, and maybe not. But you got to pull those constants all the way through. Okay, so first one people were asking about. So if you notice the first one, if you just tried to take the limit directly, cosine of 1 over infinity is cosine 0, cosine 0 is 1. So that's 1 to the infinity, which is indeterminate. So in this case, we've got to go through that whole substitution law thing. So limit as n goes to infinity of log cosine 1 over n to the n equals log of the actual limit. So you should end up with this expression. Does anyone not want me to keep going with this, or should I just do it? Then I'll give you more time to do the second and third one if you want. So I noticed looking around, some people were doing this mostly right, but maybe not getting the exact derivatives right. So if I looked at this right now, if I tried to take this limit, cosine 1 over infinity goes to 0. Cosine 0 goes to 1. So this whole thing looks like a 1 in the limit. What's log of 1? That's basically going to 0, and obviously n is going to infinity. So in balance, this whole thing is an infinity times 0 case. So then I've got to rewrite it to do L'Hopital's rule. So limit n approaches infinity. Let's do it as log cosine 1 over n over 1 over n. Now I'm basically a 0 over 0 case. So I can use L'Hopital's rule. Okay, so what we get then, and this is all equal to the log of the limit. So then we get this kind of nasty expression. The derivative of a log is 1 over the argument. So I get 1 over cosine 1 over n times the derivative of that argument. So what's the derivative of cosine 1 over n? Technically it's a sine, right? So negative sine 1 over n times the derivative of the inside function again. So that's times a negative 1 over n squared. So that's the derivative of the top. Derivative of the bottom is negative 1 over n squared. So that all just cancels out. And I'm basically left with the limit as n approaches infinity of negative tangent 1 over n. And tangent of 1 over infinity is tangent of 0, which is 0. And that's equal to the log of the limit. So then when I exponentiate both sides, I get 1 is equal to the limit. And then I should write it around the room, but the sequence converges to 1. So that's a messy derivative problem. But from the standpoint of new things being learned in Calc II, it's really not anything new, right? It's just all stuff you did in Calc 1. I believe number 2 should not be that less difficult, just a bunch of derivatives. And then number 3 will do it in 2 or 3 minutes. On the bottom?
Yeah.
Oh, well, that's just using the knowledge that, like, if I have 2 times x, right, that's the same as x over a half, right? Because if I multiply by the reciprocal, it's the same thing as, so I'm basically saying, here's what I'm multiplying with this, that's the same as dividing by the reciprocal. So that's what I did at the end. Yeah, Kevin, that actually can happen quite often with these, where a lot of them just come out to zeros or ones, so you can do a lot wrong and just kind of luck into the answer, but that actually may help people on the exam if it's just multiple choice. Okay, we'll do the third one in a minute. I'm just going to quickly put up the second one. All right, so there's the second one, which goes to 0. All right, so then let's do the third one. What did you guys, this obviously is the infinity minus infinity case if you just put the limit, so it's indeterminate. So what did you decide to do with it? What do you got?
Use the log property, so it's 2 ln plus 1 over n.
Yeah, I could combine together by log properties, and then that kind of reduces the subtraction of 2 infinite limits. So then I basically have the limit as n goes to infinity of log 2n plus 1 over n. And this I can actually just take, right? So this is the limit as n approaches infinity. Well, I could put the limit inside the log, right? Basically by that substitution law. So I want to take the limit first, 2n plus 1 over n. As n goes to infinity, you can see that it's going to go to 2 in there. Or you could divide top and bottom by 1 over n. And that would give you 2 plus 1 over n over 1, which would give you 1 over n as n goes to infinity goes to 0. So you just have 2 that's left over, so the answer is log 2. And then again, just make sure you put that sentence that the sequence converges to 2. That's log 2. Okay, so what I would imagine a lot of people felt doing this is that, oh yeah, I'm a little rusty with limits or derivatives or whatever. So, for this, just make sure you brush up on whatever you found a little bit rusty from Calc 1. Otherwise, there's really not much new from this section from a Calc 2 perspective. It's just, here's the sequence, take the limit. Any last questions with that? All right, so the last thing we want to do today is do the quiz, because that actually was a hard quiz. I think. Conceptual quiz, anyway. So basically, we had a function y equals mx on the range a to b, and we wanted to find the trapezoidal rule with 2 subdivisions, the approximation. Then we wanted to find the integral directly of what the area under the curve exactly is in terms of m, a, and b, unknown constants. And then 3 was to use the error bound to compare the first stuff in number 1 and number 2. So I think almost everyone got the second part right. So let's just do that real quick since there's not much to it. This is just literally, if I had some function, right? I don't know exactly what it looks like. M could be positive, negative, but some linear line between A and B. The question is, what is the actual area under that? Just a simple integral, so I can get mx squared over 2 from A to B, and then when I plug in, I get mb squared minus a squared all over 2. So that's the exact area under there. And obviously, if it was a different line, right, it could be this, or whatever the case may be, but that will all be taken care of in the m's, the b's, and the a's. Now, let's look at the trapezoidal rule. I'm going to write this up again, same way. Let's look at the trapezoidal rule between A and B, and it specifically said with 2 subdivisions, so n is equal to 2. So it's going to look like this. Okay, so t sub 2 is equal to delta x over 2 times the pattern for trapezoidal rule is the function evaluated at the initial spot, A, and twice all the partition points until I get to the end. I only have 1 partition spot, so I have to figure that out. And then plus f of b at the end. Now, what is the middle spot between A and B? Yeah. Yes. Okay. So what I could actually, people did this 2 ways. So even if you got this right, it might be interesting to look at it 2 different ways. Delta x, I know, is b minus a over 2, right? The width of each of these things. So what I could do to get this spot is say, well, it's going to be a plus delta x. And this piece right here is going to be a plus delta x, which is a plus b minus a over 2. If I put this all over common denominator of 2, I get 2a plus b minus a all over 2, or a plus b over 2. Now, how could we have gotten to that point logically without actually having to do this step along from one partition to another? How did we actually could have known that that was a plus b over 2 in this case? Yeah, it's the average, right? It's the midpoint of these 2 points. So we could have just said by midpoint logic that this is a plus b over 2. Saved yourself a little algebra, but it's nice to see that it works out. So either way, this is a plus b over 2. Then it becomes just a bunch of algebra at this point, because now you have to plug in these partition values to see what does the function mx evaluate to at these spots. So t2 is now b minus a over 4. A lot of people forgot that there was 2 2's here, right? Delta x over 2, and delta x itself was divisible by 2, so it's over 4. F of a is just m times a plus 2 m times a plus b over 2 plus f of b is m times b. And then let's start simplifying this down. So we got b minus a over 4. I guess we could just pull out an m, right? Let's just pull out the m. There's an m in every term. So m times b minus a over 4 leaves us with a plus 2a over 2 plus 2b over 2 plus b. Well, these are just a plus b plus b. So another 2 can come out. So m times b minus a times 2 times a plus b all over 4. And if we simplify that down, you'll get m. Multiplying this out, we're going to get b squared minus a squared. 2 over 4 just leaves a 2 in the denominator. So we see by the trapezoidal rule, the approximation of saying, instead of doing the actual integral, let's put 1 trapezoid, 2 trapezoids, and add up their area, we get the exact same area. That shouldn't be a surprise because a trapezoid will be a perfect fit to something with a linear top. Now, how do we know that? Well, using the error bound in T is equal to f double prime of C, b minus a, I don't remember. I don't really memorize these myself.
12n squared, and that's cubed.
So there's our error bound, and the important thing to note is all this is just going to kind of be nonsense because if I look at my function, f of x is mx, so f prime of x is m, and f double prime of x is 0. So this is always going to be 0. So what that says is that the biggest the error can possibly be is 0, which means there is no error, which is exactly what we saw. You should have written some sentence of explanation, but that's basically the type of thing that you would write. So any question with that? I like this because it actually makes you connect the dots of what's really going on in this type of problem, rather than just memorizing a formula. Last thing to decide for us is tomorrow's class. Does anyone have any preferences? I have to think about that.
Oh, in person.
Yeah. How about this? I'll send you an email by tomorrow morning, like 10 o'clock, and we'll decide from there. See how I'm feeling. But let's end a little early today because that's kind of a natural spot to stop. Let me know if you got any questions about anything.
Bye, Professor. Have a nice day. Stay safe.
Mark.